So we're going to look at cogging and cog compensation. The best way to solve a cogging problem, of course, would be to use a motor that's low cog. And this is a direct drive motor. It's a Kollmorgen, but it is a low cogging design. So their TBM 2G is low cogging. So it probably does not have like an iron core where, the iron is going to try to stick to the magnet that's in the motor. So like as you're spinning the motor, the magnets here get pulled on by the iron, and that produces a cog every time you go past it. So the cogging frequency would be based on your speed and number of poles. So the more poles you have, and the faster you go, like the less of the effects you feel because you're going fast and you have some inertia that tends to smooth things out. So cogging is typically something you feel when you go slower rather than faster. But I've noticed in some applications where I'm trying to like constantly run at a constant rate, and it's something's wiggling around while I'm moving at a constant velocity, and it's related to the speed and the pole count, that frequency, then it may be a cog in the motor. But these are things that we can measure. TECNOTION, another company that makes linear and rotary direct drive motors, talks about cogging in an iron core. So if it's ironless, then there'd be less cog. And if you want lots of force, then you might use an iron core to pull that flux density up. The permeability of iron would be more lines of flux than the permeability of air or other metals, perhaps. So you get more of a cogging effect. So there's a whole white paper on this from TECNOTION, it's a good read. But to compensate something, you need to measure it and then apply, some counter effect to remove the cogging. And so cogging torque is current. So if you apply a current to compensate for the cog and the torque, then perhaps you could remove the cogging. That's the theory anyways, but somebody's got to measure it. This company, HBK, they've got some interesting tools for coming up with some waveforms by measuring. And so they ramp it up to speed, wait for the disturbance to pan out, and then you look at the torque variation over time. And these would be based on your speed, but it's through the electrical cycles. So typically each motor cycle would have a similar kind of characteristic, although I guess you could have bad selection of magnets, and every magnet looks a little bit different. But the idea is you sort your magnets so that they're consistent, and you get a pretty good looking sine wave, although that's not a perfect sine wave. That's a very unusual shape based on the coils and the magnets, 2 magnets and 3 coils, repeating pattern. So these guys at HBK, they have some tools for making the tables and measuring things, and they can very sensitively measure the torque. That's good. So we're going to see what Copley can do about this. We have some new features for cog comp based on phase versus position after homing, so slightly different types of cog compensations. Just to show you, on our web page, there's a note for the compensation under support, general, application notes, and it's encoder corrections table. So, with a laser, you can do position correction, but with the torque measurement, you can do cog compensation. So motor cog comp based on the phase angle. And there's a bunch of details in here. So read the note, app note 126. So anyways, I've got a motor. It's a Sanyadenki motor, and it's 4 poles. So every rev will have 2 electrical cycles, and the phase will repeat itself, and you see a consistent repetition of the bounciness between phases. I tuned up the current loop for about 1 kilohertz of current loop bandwidth. I got velocity nice and stiff. I moved my pole out to 100 hertz because this frequency at this speed is a low frequency. As you go faster, it becomes a higher frequency, but as you go faster, your inertia tends to help smooth you out. So you typically only see cogginess when you're going slow, and you don't see it so much when you go fast. So I'm concentrating on a slow speed, which is 120 RPM. Ramp it up, run it. I got to get away from the bounce for the disturbance and get some good data. So this is tracing profile velocity, following error. The error is plus or minus 5 counts, maybe a little bit less. So it's tuned up rather nicely. I got pretty stiff gains here for the VP and VI, and then the PP at the default. There's no load condition, so maybe this is the best way to do it. No load. Actual current. Current is torque. So as the error builds up, then the current builds up. As the error goes up, the current goes up. So the error, and if the error was 0, what would the current look like? So it would probably be something like this, but with maybe a slightly bigger or smaller amplitude. You can zoom in and you can measure between the peak and the low and get the delta. It's like plus or minus 25 milliamps. Anyways, this is the move without a cog comp. And we've got this very cool tool now under support, under general, under software, motor cog comp software. And so what I've done is I've made a trace where I gather a good phase, motor phase. This is the motor phase angle from 0 to 360, a pair of magnets as we're going by. So I start the move, the bounce goes away from the disturbance, and I'm at steady state. I'm at 0 following error, plus or minus like 5 counts, and then I got this current. It's viscous plus the cog. So the loop is trying to compensate for the motor's cogginess, and it's not bad. It's just not perfect. So run the software. The save to a file will produce a comma-separated value file. I could make sine waves and apply them. Is it 2 bumps per rev? I mean, if it's a perfect cog with a perfect sine wave, this will work too. But this is kind of in the mud a little bit here. So the mud looks kind of like a sine wave, but not really. And so we select the file. I put it on my desktop. It's cog test number 6. There's the data. Let's give it 25, plus or minus 25 for 50 milliamps. I could shift it this way or that way a little bit. Maybe the current comes after the error, so I could shift it that way a little bit and have the current lead. But let's just go with it with sort of the default, create the file. You get a little file with the sine waves in it. That's very nice. And after you create the file, then you can load it in with CME, so correction table. And then you open up the file. It's on my desktop. It's that file right there. I've already got it in here, so go to cog compensation for motor phase angle. This is all populated from that file, and here's the table that's loaded, and I'm going to save it to Flash. Okay, now we don't have to make your table. You can make your own table, right? So go to that company, HBD, these guys, HBK, and give them lots of money, right? And they'll make like a laser company for measuring position, and this company for measuring the torque, very sensitive torque measurements. So we're giving it to you pretty sensitively within the tens of milliamp range, but let's see, we're going to make the same move again, and the following error. There you go. So this is the current actual current, and it's being applied per phase. So assuming all the magnets are the same, you can get your following error down to plus or minus. There's plus 1 count, minus 1 count. There's an occasional 2 in there, so nothing's perfect. That maybe it's the bearing, right? You got to blame somebody, blame the bearing. But what we've done is compensated for that motor's inherent cog. Now, it's not a cheap motor, this motor. It's reasonably priced, so it's pretty good. The cheaper stuff you buy, the worse it's going to get, or iron core, lots of force, but lots of cog. So it really depends a lot on the application. This is a file that you would have to save and load. That would be a CCE file. It's not part of the CCX file, although if you're using the latest software and latest firmware, the CCD file is pretty reliable. It's designed originally for EtherCAT loading the configuration with FOE file over EtherCAT, but it's an XML file format, but it's a copy of Flash. So in the CCD file, not only do you have the drive parameters from the object dictionary instead of the parameter dictionary like ASCII, you get the object dictionary like DS402. It also has a copy of the Flash. You can't read it, you don't know what it says, but you can load it, and then you can go into here and then see what the table looks like, and then save that to a file if you want. But I guess maybe each motor would be slightly unique. Hopefully not. Hopefully they all have the same cog. If they have the same construction, they should have the same cog. So do you do this once per drive motor combination in an application, or would it just be used across the motor range? If all the motors, like this is a Japanese motor, so they're all going to be identical. If someone has a poor construction technique for making all their motors different, then you'd have to make a unique file for each one. Better just to buy a motor that's low cog in the first place and not have to try to compensate for it. But that's it, cog compensation. Big thanks to Anthony for writing some software, and CME guys for getting it into the software release candidate 2. This is the 8.1 release candidate. Everything seems to work. Feature looks great, and thanks for watching.